An interesting thing happened when Thomson put neon gas into the cathode ray tube. He observed 2 glowing dots on the screen instead of 1. Each dot corresponded to a unique charge-to-mass ratio. That is, he was able to calculate 2 different values for Q divided by M. Thomson concluded that different atoms of the same element could have identical chemical properties, but have different masses. Each of the differing forms of the same atom, with the same chemical properties but different masses, is an isotope. A device similar to Thomson's cathode ray tube that is commonly used to study isotopes is the mass spectrometer. The mass spectrometer is able to precisely measure the charge-to-mass ratios of positive ions. From the charge-to-mass ratio, the mass of each isotope can be calculated. The material under investigation is called the ion source, as it is used to produce the positive ions. The ion source must either be a gas or a material that can be heated to form a vapor. The positive ions are formed when accelerated electrons strike the gas or vapor atoms. The collisions knock electrons off the atoms, forming positive ions. A potential difference, V, between the electrodes produces an electric field that is used to accelerate the ions. Here you can see one type of mass spectrometer. To select ions with a specific velocity, the ions first are made to pass through electric and magnetic deflecting fields, as in Thomson's cathode ray tube. Ions that pass undeflected through these 2 fields then move into a region that is subject only to a uniform magnetic field. There, the ions follow a circular path. The radii of the paths can be used to determine the charge-to-mass ratios of the ions. The path radius, r, for an ion, can be calculated from Newton's second law of motion. Solving for r yields the following equation. The velocity of an undeflected ion can be calculated from the equation for the kinetic energy of ions accelerated from rest through a known potential difference, V. Substituting the expression for V in the equation r equal to mv divided by qb gives the radius of the circular path. Simplifying this equation by multiplying both sides by b yields the following. This equation can be used to determine the charge-to-mass ratio of an ion. Here you can see that in one type of mass spectrometer, the ions strike a plate of photographic film, where they leave a mark. The diameter of the curved path traveled by the ions in the vacuum chamber can be easily measured because it is the distance between the mark made on the film and the slit in the electrode. Therefore, the radius of the path, r, is half of this measured distance.